next talk is by Ivan on Lagrangian formulations. So please, go ahead.
Well, first, let me thank the organizers of this program who have given me the opportunity to explain here this work, which was born when Felix visited us in Madrid last spring. This is the outline of the talk. I will try to give a rather detailed motivation for the work and to make clear the objectives. I will introduce the basics on phase-space Lagrangian formalism and the implementation of the gyrokinetic ordering in it. Section 3 contains the main calculations and results. Later I will make very brief comments on gyrokinetic Poisson equation and ordering, and I will go to conclusions. The setting of the talk will be this one: time-independent magnetic field. Okay, so only electrostatic turbulence, and we only deal with dynamics of ions. Extensions of this will be tackled in the future. So first, some notation. Denote by L the macroscopic scale given by the typical length scale variation of the magnetic field, Vt the thermal speed, rho I a typical ion gyro radius, omega typical gyro frequency, and phi the electrostatic potential. When one speaks about gyrokinetic ordering, one understands something like this: that epsilon, defined as rho I over L, is small, that the electrostatic energy is much smaller than the thermal energy, than the kinetic energy, ordered by epsilon, that the fields, which I write here in particular for the electrostatic potential, have a very the Fourier transforms in space and time are localized in very concrete regions of space and time. So typical wave numbers are in the perpendicular direction are of the order of 1 over rho I, and in the parallel direction of the order of 1 over L. And for omega, the typical omegas that one wants to resolve when compared with the gyro frequency are of the order of epsilon. And however, modern derivations of gyrokinetic equations are carried out by performing two independent expansions. One, a guiding center expansion in rho I over L, and after that a gyrokinetic expansion in powers of parameter epsilon sub phi, giving the size of the electrostatic fluctuations. Okay, and as Dimit said this morning, we want to sort of collapse those two parameters, implement just the gyrokinetic ordering, define it in terms of epsilon, and carry out the calculations at high order. Okay, which is summarized here. We'll implement this the previous gyrokinetic ordering, which is defined only in terms of epsilon, in the phase-space Lagrangian formalism. Carry out the computation of the Lagrangian phase-space Lagrangian up to order epsilon squared. And in particular, we will give a fully explicit expression of the second order Hamiltonian in general geometry, of course. We'll see how the calculations and the results are much more complicated when one carries out the expansion this way, the orderings this way. And we will learn basically that if one wants to implement strictly the gyrokinetic ordering, guiding center and gyrokinetic dynamics are inextricably tied together, and new terms appear that are absent in the customary derivations.
So in your previous slide, most people wouldn't express, most derivations I've seen wouldn't explicitly say that they're doing two expansions.
Mm-hmm.
Well, I mean, a lab might say that, wouldn't he? Does he, wouldn't you?
Yeah.
I think
Because
it's,
you do it first for the magnetic and homogeneity, and then later for the potential.
A lot of the papers just take the first one as done and just start from there.
Yeah.
yes, it's sort of, yeah, that's
Sorry,
approach.
speak up, Anders.
A lot of the published papers just take the first one as done and start from
Yeah.
there. And just
So the second parameter is kind of,
You'll get the second time.
Essentially, the formal turbulent calculation starts with the perturbation of the guiding center.
that's the standard approach, and I want to see what comes out with when one implements strictly this.
So there's old-fashioned derivations which do an asymptotic expansion in a single parameter. From the beginning, they order both the size of the potential E phi over T and the variation of quantities like V. So they do 1 and 2 together at the same time.
That's why it says mono derivations.
Yeah.
Okay.
And let's
Okay.
see what we obtain.
But
Yeah.
but there is nothing that formally prevents you from combining those two small parameters.
No, of course, no. There is nothing preventing it, but you agree that the results available in the literature do not allow to collapse those parameters and obtain the correct result at second order. Okay, that's what I want. We wanted to perform an explicit calculation and show that in principle, if one strictly implements that gyrokinetic ordering, that old, let's say, gyrokinetic ordering, and wants to obtain.
I should point out, however, that I believe that I did include the combinations of both guiding center and gyro center in my dissertation. Even though it's not published literature, it is publicly available.
Well, okay, you can see it and we can compare results. Well, first, I introduced some of the basics of this phase space Lagrangian formalism, which is briefly described as follows. And you take a dynamical system defined by a Hamiltonian and the canonical Poisson bracket. Then one can obtain the Hamilton equations by making stationary this functional, where L is the Lagrangian, but expressed in different variables from the standard Lagrangian mechanics. Okay, here is viewed as a function of all coordinates of phase space. So this formulation, which is now standard in modern derivations of gyrokinetics, has the beautiful properties that combines the scalar invariance and variational principle from Lagrangian mechanics and the flexibility of coordinate transformations in phase space from Hamiltonian mechanics. And well, a particular case, which is the Lagrangian of a charged particle in an electromagnetic field, as everybody knows, is this one. And in order to implement the ordering, we non-dimensionalize variables, which is rather convenient, and this term in red expresses the ordering in the size of phi. And as for the characteristic perpendicular case, we introduce it formally the following way. We want to introduce the fact that the ordering of the derivatives is like this, so we write this for phi hat. Okay? So this Lagrangian with the epsilons given here and this functional dependence of phi hat is what we are going to transform to carry out to work out the gyrokinetic Lagrangian at second order in epsilon.
So this is a completely ignorant question, but maybe there's some others in the audience too. So I've usually seen simple Lagrangians as functions of Q and Q dot, or R and R dot.
Mm-hmm.
Here you have an extended set of variables,
Mm-hmm.
because B and R dot are not independent.
Mm-hmm.
So
This so,
what's the advantage of this formulation?
Yeah,
Why is it done
Greg,
like this?
Greg, what you said is incorrect. It's R dot and P are independent, or R dot and V are independent.
yeah.
R dot is equal to V only after the variational principle, not before.
So one way to think about
Here,
it is if you
what
do-
you are treating as independent are the Q's and P's, and Q depends on Q dot, and P on P dot as Q and Q dot depend in the standard Lagrangian formulation.
But
So
the
the
standard
usual-
Lagrangians I've seen, I'm trying to learn this stuff, and it just
Mhm.
expresses L as a function of Q and Q dot. There's no P
That's
in
the
it.
standard, yeah. That's the standard.
So what's the
And
advantage of
then
this?
you obtain Lagrange equations. And as a matter of fact, well, this is sort of standard stuff, for example, in the book of Goldstone. The point is that if you establish, well, there is a geometrical version of all this in which you see the Lagrangian as a function in the cotangent bundle of the mechanical system. But from a practical point of view, the point is that if you present this like this and you do variations, you actually obtain the Hamilton equations. I don't know if that's very satisfactory. The geometrical way is the way to understand it more
low
deeply.
tech
But
The beauty of the Lagrangian here is that if your H is independent of Qi and Pi is independent of Qi, then Pi is a constant of motion.
So the low-tech answer would be that the Lagrangian you're used to, you get a second-order differential equation in time, whereas here you get a pair of first-order equations.
yes, of course.
This gives you the Hamiltonian form as Pi dot equals something, Qi dot equals something, whereas the L of Q and Q dot gives you something like Q double dot equals something.
In the standard formulation, you define the canonical momentum as dl dq dot, right? So how is the momentum defined in this language?
Well, here,
Same way.
well, I don't know.
Will it be dl
Maybe
dq
we
dot
don't-
or dl dp?
No,
It's
it's
not-
the LDQ dot.
It's not,
Which is P, you can just see from that.
Here, you should, I mean, for the purpose of this talk, you should assume that you have a dynamical system given by a Hamiltonian and a canonical Poisson bracket, and that's the standard way. Probably the natural way is that you first have a Hamiltonian, have a Lagrangian, and then you define the momentum, you compute this Hamiltonian, and then you compute the phase space Lagrangian like this. Well,
The key point of this phase-space Lagrangian is that it can only be linear in dotted quantities. One of the single problem with the so-called Taylor guiding center Lagrangian is that it was quadratic in some dotted quantities, which made
sort of,
it invalid.
when you find the stationary points, then you have solved for the velocities, let's say. In the Lagrangian formalism, you usually have to solve for the time derivatives, and here, well, you obtain directly Hamilton equations. So, but the most useful property is scalar invariance and the possibility to make coordinate transformations in phase space without having to independently for P's and Q's. You have sort of both advantages. But
Okay.
so we were here. This is the Lagrangian with the epsilons formally implemented in it, and we want to carry out the gyrokinetic computation up to second order. And so now we go with our computations and results, and well, you see that the computations are quite horrible. I mean, they are really cumbersome, and I would like to be very clear in stating the spirit and the strategy of the computation. I will also present some intermediate expressions just to have a taste of what's going on. But of course, it will be impossible to follow the derivation in detail. And I will finally present a result which sort of shows what we wanted to make manifest. Okay, and well, in this phase space Lagrangian formalism, one has so to say two tools to play with and obtain equivalent Lagrangians, and those are change coordinates in phase space, maybe time dependent, and the addition of total time derivatives, okay, which of course do not change the equations of motion. Applying both transformations, you obtain a transformed Lagrangian in which, in principle, both parts, the symplectic, I'm calling symplectic the part which goes with velocities, in which the symplectic and the Hamiltonian both get modified. So one can play with these two ingredients in order to impose the desired conditions on the gyrokinetic Lagrangian, if they are achievable, of course. So a rough way to summarize things is that in gyrokinetics, one wants to find out whether there exist coordinates r, u, mu, theta, and a gauge function s, such that the transformed Lagrangian is gyrophase independent and mu is a constant of motion. Okay. And in our concrete case, let me say that for technical convenience, we'll write the.
Whoa, you're. I don't like the prescribed preparatory change. That seems very much like a guiding center transformation to me.
Oh, well, you'll see, and it's very similar actually. Yes, when you see the.
So it is a two-step process.
No. Well, we can call it whatever, but we'll do of course, we have to go from the canonical variables to some variables somehow adapted to the magnetic field.
Shall we call them guiding center coordinates?
Well, let me see.
Well, maybe you
And keep-
call them zeroth order guiding center.
And we will keep everything up to the desired order we want to obtain in the end. Okay. I'm
I
not,
guess
of course.
the difference must be whether you do or do not. I mean, if this is an exact transformation, right? It doesn't involve the perturbation.
No. The difference is that we are going to keep everything up to the order we want to arrive at the end.
The T1 isn't the transformation to the lowest order guiding center variables. It's actually the Lie transform, one that already starts to remove gyrophase dependencies.
Yes.
I guess the point is that you.
Well, I will show you the
you're
transformation.
removing gyrophase dependencies.
But
on-
you could, well,
you know,
well, we can discuss it at length. No problems. Well, of course, I'm not doing. Well, okay. And so, you see, T1 is a change of variables we find convenient, but anyhow, we'll keep, of course, every the terms up to order, dropping only terms of order epsilon q. And T2 is the change of variables will be determined order by order by imposing the gyrophase invariance of the Lagrangian and the conservation of mu.
So can I ask then, the T1, it's not a, is the T1, I mean, to go, is that from it's not from X and V to just your lowest order guiding center? I mean, is it
sort of? I mean, it coincides.
The question is it perturbative or non-perturbative? I guess. Well, you'll show it.
Yeah.
That's what I said.
The first,
Sorry.
the first one is exact. Well, I advanced some things. I mean, the first one is exact, but of course, if B is non-constant, then A depends on the variables, and well, you have to expand A, and we will keep all the relevant terms so that we can then start extracting the gyrophase dependency with the second one. Well, one could of course avoid all this, but there were kind of we think nice cancellations doing it this way, and well, we found it rather convenient for us. But of course, I have to say one can combine both transformations at the end, and if one wants, one doesn't want to show it as a composition of transformations, then there is no problem, and one can be sure, and one can make sure that one is not losing any term of order lower than epsilon q. Just two remarks are maybe in order. That we're not using a geometrical formulation, more than a geometrical formulation, we're not using geometrical language. But for all those familiar with the language, I think that it will be more or less obvious how to translate every step of the computation. And here it's just a notational remark. It turns out that I want to sort of show finally a fully explicit expression of H2. That was the exercise we wanted to do. And when one does the computations, it turns out that in order to give a fully explicit expression of H2, one has to determine, of course, the Lagrangian at order epsilon square, but the term with d theta one has to compute at order cube. So we will use this kind of notation later, in which I mean that I'm dropping terms, only terms of order epsilon cube, except those terms which go with d theta, which I'm computing one order higher, just to make everything precise.
So if you go back, you're going to compute the new mu not only to first order and second order, but you're going to keep also third order terms in the definition of mu.
Well, we can compute the correction to order epsilon square of mu.
But that's not what you just wrote.
Yeah.
So
It appears when one annihilates the coefficient which goes with epsilon cube with the theta. That's what
in the
appears.
normalization that we had, there is an epsilon in front of the mu d theta dt.
Okay.
The mu2 correction goes with the cubic term in d theta. Okay. Well, this is the first change of variables about which we discussed before, and more or less everybody could guess. Okay, in which we sort of do an infinitesimal part of the job, in which we take a sort of starting gyro center, position V parallel, mu parallel, and mu and gyrophase, okay? And we simply, a good idea or not, but we plug it in the Lagrangian, okay, and keep, of course, all the terms coming from the expansion in A to the relevant order, okay? And, well, yes, a function which makes things
Do you
nice,
have an
okay?
expression for V parallel sub G?
V parallel sub G, yeah, well, it's V times this. I mean,
That's not a transformation. You have
why not?
to. So V parallel sub G is V dot B hat.
Mm-hmm. Mm-hmm. So yeah, we're taking.
No, you don't need.
May I continue? Or?
Yes.
Okay. Well, so this is the first monster, okay, which you can. Well, I wrote here the expressions to see that it's very complicated and that, but okay. You can take this the Lagrangian, in which now we want to eliminate the gyrophase dependence and impose the constancy of a modified mu.
So far,
Mm-hmm.
you're really doing the guiding center transformation.
Oh, we're doing, well, whatever.
So it's the first step.
Well, whatever. I mean,
Yeah, but don't tell me it's a single step if you do two steps.
well, first, I think I probably, I don't know if I use the word, but I didn't want to use the two-step expression. I mean, one step or two steps is kind of semantics. What I wanted to say is that we are going to do the expansion at second order, keeping everything. That's
So
whatever.
at this level, it's non-perturbative. You still have the
Mhm.
H1 and the
Everything.
gyrophase dependencies there, and the one step is removing those gyrophase dependencies together.
I haven't removed anything. I mean, it's there is everything up to the order written in the last part here. Okay.
Now,
So
you
like-
also have gyro gauge dependent terms in your expression. Are you going to say anything about how they're removed?
Yes. No. We will find. We will end with a gyro gauge independent expression. Well, I advanced again that for our final Hamiltonian, well, there are some freedom in which gyrokinetic Lagrangian, you want to end up. You have some freedom, and we chose that to stick to the modern literature in order not to amplify the confusion. So we'll end up with the standard symplectic part for the Lagrangian, and all our differences will be in the Hamiltonian.
Could you go back a few slides and show us what mu g was? So, okay, mu g is sort of hardwired to be whatever it is.
Mm-hmm.
So mu g is not the guiding center magnetic moment. It's really just the kinetic energy, the perpendicular kinetic energy over 2b, or over b. So it's the lowest order magnetic moment.
At the capital R position.
Sure enough.
Okay, and well, now with this sort of good idea or not, starting point for our variables. Now we want to find the modified r, u, mu, theta to the required order, so that the Lagrangian is phase invariant and mu is a constant of motion. And well, the standard way is to write it, the operator as a Lie transform, which has some advantages certainly, although will not take much advantage of it, and we will find some different variables more useful. But anyhow, I write here the equivalence. These tilde variables are more useful when doing the actual computations, which keep the order of the transformation. Okay. Okay. Well, I just present here the second monster, okay, which is this general change of variables acting on the Lagrangian. And well, now one wants to see if one can solve for all these corrections and satisfy the imposed form of the final Lagrangian, which I will give. So the complete question is if there exist gauge functions, which is the degree of freedom we still have. There exist gauge functions of each order, so that the Lagrangian is of this form, okay, just the standard form in the literature, but with an order higher in the Hamiltonian. Of course, here there is no epsilon squared term because we have the freedom to make it 0. Okay, we wanted to do that in order to keep close to the literature. I mean, the freedom we have in the change of variables allows, for example, to make 0 higher order corrections here and put everything in the Hamiltonian. So the question is, if by imposing this form in the Lagrangian, there exist functions S, so that one can solve for the change of variables and the gyrokinetic Hamiltonian. And of course, there exist. I write here the lowest order corrections of the change of variables, and I don't write the next order ones, which I think it will be one slide for each. But I think in order to make the point of our calculation, it's much better to show the fully explicit expression we obtained for the second order Hamiltonian. Okay, the 0th order Hamiltonian and the first order Hamiltonian are very well known, of course, and it is in the second order Hamiltonian where things sort of exponentially complicate when there's the expansion keeping all terms. It's here. These two first terms are, I would say, the standard terms, and the other ones, well, of course, these are phi. This is why they always appear in the standard literature. And these ones, these 3 lines here are phi rho. That's why, okay. And these ones don't have rho and phi because they come from explicit gyro averages we were able to do, okay, containing only functions of rho.
Sorry, could I just ask you, there are quite a few people in the room who have their own gyrokinetic Lagrangians. Do you guys all agree on these terms?
Isn't that okay?
Yeah, well, that's, you know, I'm not in the business, so I just want to know what the, you know, at this point, do you agree?
Well, I
That's
could
what it
write
looks like?
these terms all quite concisely and succinctly with the 2-step approach,
Yeah, but there's,
I could combine a lot of terms in terms of Poisson brackets and so on, so
so you're saying you can't parse this.
yeah, I could.
So far, these are the same terms that you have and that
Well, I think what it's saying is that he has expressions for them, but I think most people do not have all of these terms explicitly.
yeah, but that's just,
Second
I'm not asking about the form in which you're going to write them. I'm saying
Sorry,
if I were to unpack Alain's expression or somebody else's expression, will I be able to sort of tick mark every one?
You
of these
should.
terms?
No,
Yeah.
wait. The cross terms.
Can I ask
between
the speaker whether that's true?
Well, I don't want to say what one can do or one cannot do with his expressions. I mean,
No, but isn't-
I would say
isn't
this.
Isn't
I
it
haven't
true
seen
that-
this, but
that the
that's all I
cross
can
terms-
think.
The cross terms between the potential and the magnetic inhomogeneity are usually not kept in most of the theories.
Why?
That is correct.
Why?
Because
Because
they
they are
don't
cross.
come out naturally if you do it, I hate to say it, but in the two-step perturbative procedure.
Yeah, but this is a discussion about method, right? In the end, there's something that's claimed to be a physical object, which is a second order Hamiltonian, and it has to be the same for everybody, regardless of the route by which you have.
Well,
arrived.
only if you do the expansion, keeping all the terms. I mean,
Yeah. So you're saying this is the expression going up to epsilon squared, right? Period, right? Let's forget how you derived it.
So most derivations, at least some of Texu's derivations, he expands to second order in rho over L, where L is this gradient scaling for pressure or density, but only first order in rho over R, the scale length of the magnetic field variations,
There's an aspect
That's
ratio
true.
expansion.
that's true.
essentially. Or you're in the vicinity of a transport barrier where gradients are much steeper than.
In the standard, what I will say is that in the standard derivations, if you collapse those two parameters, epsilon, I don't know how they are usually called, epsilon b and epsilon phi, you cannot collapse them into an epsilon and say that you have correct epsilon square
Well,
terms.
I would think you should be able to if you did the expansion to second order.
Ah, of course,
and
of course, of
epsilon
course,
B.
of course, of course, of course,
Well,
of course. Yeah, of course.
Greg, sorry, but
That's what we have done in the end.
what you've just said, does that only apply to second order terms or also first order terms?
The corrections only to second order terms.
No. So Greg said that basically what Greg said is that this is, if we take this set of terms and then throw out in that last expression H2, throw out everything that can be under some subsidiary order in aspect ratio, right? It'll simplify somewhat. But are you also going to apply that subsidiary ordering to H1?
H1 is fine because there's no problem with it. Everybody kept H1.
No, I understand, but that's going to be.
I don't know,
Can
I
you
don't know.
can you tell me in H1 what is the argument of phi?
The argument of phi in H1, yeah, hopefully, let's say.
I mean, it would be nice if, as a result of this slide, there was some agreement or disagreement about what the starting point is for the rest.
Well, I mean, isn't the problem, if I understand it correctly, that if you first do the magnetic inhomogeneity, even the second order, at that point in the theory, you do not have any phase dependence left. But in fact, these
First
second order
order
cross terms that he's getting involve phase dependence that comes in at first order in that magnetic expansion and first order
Yep.
in the potential expansion. And
So why? Yes, but that's what
Well-
happens when you start doing second order expansion.
no.
Say,
No, if you complete, suppose you do
No,
the
how to
magnetic
write it
inhomogeneity
well.
first, second order, or third order, I don't care what. You now have some sort of starting point for your next step. But it's a Lagrangian or Hamiltonian that has no phase dependence in it whatsoever. You can't possibly get then any beating between phase dependence related to magnetic homogeneity, and phase dependence related to the potential.
Is there an actual unique correct expansion?
This is probably it, I would think.
Okay. So so everybody's on the same page. This is all fine,
So
Well,
right?
one check that should be done is that just the magnetic pieces up to that order without the beating terms, do they agree? Is there consensus at that order in the guiding center
We
theory?
have tried to look for these things
Yeah.
and no one has published them.
I don't know.
The second order corrections to the Hamiltonian due to the
I mean, some of them were even done by Little John, just selectively, I think.
yeah.
I think this is
So what you wrote down here, you had phi, which was a function of r, capital R plus epsilon rho. Now this rho, what is the physics of the gyro radius? Is it the guiding center gyro radius? Is it the gyro center gyro
yeah.
radius?
It is the functional form
What is
of the.
Does it depend on electrostatic potential, you're asking?
Yes.
Well, of course, what I have written here enters are at first order. So at first order, only the let's say the standard form of the gyro radius counts. The form, well, you already know what will be the guiding center gyro radius. This.
Okay.
Okay.
So all the other non-uniformity terms could be related to corrections of the guiding center gyro radius due to the magnetic field non-uniformity.
Yeah, I think it will be
that what most
a
of
way
these
to
terms almost
state
will
it.
Yeah.
But that's the point
It
of
will
the
be,
calculation. isn't
yeah,
it?
that's the point.
Except,
But
except there's one term there that I don't, in the 1, 2, 3, 4th line, the last term, that doesn't seem to have a gradient of the magnetic field in it.
Which one?
Yes, there's
Which
a
one?
there's a gradient of
Where's the
b
one?
hat.
There is a gradient?
Outside.
In the front, there is a grain of behind.
Where I don't.
Ah, thank you, I missed the
fourth
double, thank
line.
you.
Yeah.
All right.
It's answered.
So those are all just the magnetic geometry coming in and being treated at the same footing as the
I mean,
fluctuation.
I'm not. Of course, I'm not saying that the result is unexpected or extremely interesting. I don't know, but we wanted to do the computation explicitly and show that if one carries out the computation up to second order, it doesn't make much sense to in the end of the day to speak about gyrocenter or gyrokinetic dynamics separately. Well, there are terms which tie them together. And
So we now come to the in my view the physical motivation of this work. When you look at the polarization effects, you're going to take the functional derivative of the Hamiltonian with respect to phi. H1 will give you the guiding center polarization, which is essentially the Laplacian of P perp. But that does not involve the magnetic field non-uniformity. The more standard H2 terms will give you the gyrocenter polarization. So the new terms will involve corrections to the guiding center polarization that involve the magnetic field non-uniformity.
sort of, yeah. The new terms will not involve phi, of course,
That's right.
because that's. I mean, there are. Because, of course, the functional, as you perfectly said, functional derivative acts here and gives terms linear in phi. Here gives things without phi, only with geometry. And apparently all these terms do not enter there because they don't have phi.
So
Those will be the correction. But I would like to
So
see
what is
more.
the physical meaning of the terms that do not involve
No,
phi?
that's I want to because we were talking about this this morning and we came to the same conclusion that these terms at that level seemed not to contribute, but well, at least in that equation. Of course, in the equations of motion, they contribute. That's
Yeah,
that's,
but the,
that's
in
clear.
the-
But in that equation, it seems not.
But in the equations of motion, they'll enter at epsilon q because they'll be affected by gradients.
No, because you have these are these has parallel gradient. It's actually affect the parallel velocity to second order.
In the equation for the parallel velocity, they enter to second order.
They come to second order. Yeah.
Now, if one wants to do it consistently, everything at second order, you can. I think you cannot drop it. You can find some place where they will enter.
I don't know whether this is an intelligent question or not, but I'll try anyway. Suppose you try to write down, or you could write down your gyrokinetic equation using this H2. And you went off and you took moments of it. And somehow you did conservation of toroidal angular momentum. How much of the off-diagonal stress density you get? Is that obvious? It's certainly not obvious to me. But.
Oh, no,
What do you want me to answer?
Obvious. Okay, then it won't be obvious to me.
The other thing we also
I
need,
won't feel that.
but according to you, Peter, we need H3 and H4
I don't know.
for that as well, right?
Huh?
Well,
Don't we need H3 and H4?
I'll talk about it in the next talk.
yes,
I can compute it
I
next
know,
week.
I think
or-
we're going to see
H3, I think it's H3, H4. I think only H3, but this is
only
going to be-
H3.
but
Yeah.
you know, I obviously don't do it this way. I guess I now know why. But it's a bit distressing because the years.
Yes.
I'm sorry if this is showing an unappealing side of my personality, but the years I've had thrown in my face that modern gyrokinetics gets everything much more easily than the old-fashioned way. This doesn't look easy to me.
Well, it's not my problem.
Yeah, okay.
I guess we should continue.
We'll continue with probably much less interesting comments, but those are my last two slides. I want to make only a couple of brief and probably not very original remarks on the gyrokinetic Poisson equation. The Poisson equation in dimensionless variables is this, and we make the pi length much less than the gyro radius, and this hypothesis, okay, that the gradients of f are of order 1, then one obtains this expression at first order. Okay, I'm writing it only at first order. And this delta function, which of course for explicit computations one should integrate, and if one integrates it with care, leaves a subsidiary Jacobian, okay, which is like this.
Let me
But
ask a brief question. So are you telling me with the definition of your B parallel star that this is the entire Jacobian for your full transformation?
Here, well, since I wanted to be very sort of precise, in this one, since I am writing here the Poisson equation only at first order, I'm keeping only this B star, which is the same as yours at first order. It's B parallel plus the term with the parallel velocity. It's only this.
But I thought that you were keeping terms of
Yeah,
order.
but my last two slides are sort of separate from the other. Of course, we have computed everything at second order. I could keep it and write it, but since I just wanted to make a couple of comments, maybe it was a bad idea if this is going to confuse somebody. But for the small comment I wanted to do, I only had to write it to first order.
Don't you get first order terms from the second order Hamiltonian? Only?
What?
You're differentiating the second order Hamiltonian with respect to phi, so.
Yes. Oh yeah. No, that's not an issue. I was just surprised to see the simplicity of his Jacobian.
Mm-hmm.
But he's not obtaining the equation from taking the variational derivative. He's now doing it direct.
I have simply
Transformation.
made the change of variables here. I mean, I want to write this in the, I have simply written this in the gyrokinetic variables. I have, well, sort of taken the pullback, if you want, and applied only the and of course this is well, if you want of let me call globally x or set are the gyrokinetic variable, and then here as well. I'm sort of symbolically writing it. I don't want to do it very complicated. Okay, and this thing is what you will obtain from the Blasov equation in the gyrokinetic variables, and that's what I'm writing there. I mean, I'm just applying the change of variable formula to the integral. This is,
So I'm trying to understand this. What happens to the energy constant when you do this?
I didn't worry about this. I mean, we have finished it last week, the
Just
calculation of the
generally, I mean,
H2, so.
Elaine, maybe you can answer. I mean, if you let's proceed from the second order Hamiltonian to get the energy constant right, would you keep? What do you do about the Jacobian? I mean, does that have to stay at second order accurate, or?
Well, if you carry out the transformation to, well, you know, the B parallel star here that appears here is what you would get by ignoring terms of second order in your transformation.
But I mean, to get an exact energy constant,
then the only requirement is that the Jacobians satisfy the Liouville theorem. Namely, the time derivative of the Jacobian must be expressible in terms of an exact divergence in phase space.
That's guaranteed by the formalism.
That's true, whatever or wherever you truncate.
yeah.
That's guaranteed by the formalism, by the fact that you're employing sort of a one form, which is, well, technically a one form which is closed and gives you a Poisson bracket, so conservation of some volume one form.
I thought you promised you weren't going to use geometric language.
Well, but yeah,
It's hard.
like not too, but if you,
Okay, go ahead.
nobody's going to believe me if I don't say it in the, that language.
Sorry, so this is the one slide you have on this, or is there another slide?
Sorry?
Is there going to be another?
Well,
slide?
yeah, there will be one more, just one more.
Oh,
Do-
maybe I should wait till.
But okay, just maybe I shouldn't have included this Poisson equation comments, but well, from here to here, we have simply integrated carefully the delta function, which leaves, as I said, a Jacobian here, one more, which is actually a submatrix of the matrix giving that Jacobian. And it's, however, interesting that one assumes that F is, if one can expand F as a Taylor series in epsilon, then the Jacobian just does not contribute at first order, and one obtains a rather standard expression for the gyrokinetic equation, gyrokinetic Poisson equation at first order. And I would like also to stress, which is I find sort of nice, that from this expression one actually deduces how this gradient has to be ordered. I mean, one does not have to impose this behavior of the perpendicular gradient of F1 as a hypothesis, but one deduces it from here, because otherwise this equality cannot be kept. Okay? You can take a perpendicular derivatives of this expression, and if this is not the case, you cannot keep this. And well, just to conclude. Well,
I had a
okay.
question then. Does this recover that second term in the Poisson equation, or are you assuming there's also the grad capital phi tilde dot b hat dot
Sorry. What?
The grad capital phi tilde dot b hat cross grad f term. It's also there, sort of formally.
He's talking about R2.
That's the
Is that
second
R2?
order.
Ah,
That's the second order term.
Second order term.
that's
So they keep it
that's
right.
here is
Yes.
second
He's
order.
not taking
In
this.
this order, it's second order. Okay. I mean, with the results we could write, as I said, the gyrokinetic Poisson equation to second order, but I just wanted to make a couple of small comments, and I think it would really be terrible, the aspect of that, the appearance of that formula, but we'll write it at some point. Well, just to conclude, we have formulated a gyrokinetic theory with a single expansion parameter epsilon, which implements the sort of standard gyrokinetic ordering, and explicitly showed by giving a fully transparent expression for the second order Hamiltonian that guiding center and gyrokinetic dynamics cannot be split. And well, we have computed, as I said, the epsilon squared term of the Hamiltonian, and just a comment that I didn't make before, by setting phi equals 0, we get for free the guiding center Lagrangian with 0 electrostatic potential to an order higher than at least to our knowledge,
That is not
available.
true.
No?
That's not true.
Okay. Can show me the reference. And as next steps, if we are strong enough, we will try to work out the electromagnetic case, include external flows, and of course some sort of discuss, which I think partly we have been doing during the talk, discuss the implications of this. And that's all. Thank you very much.